Okay, so now we need to take this to the next step, okay?
More lost than already.
Yeah, you will. So, up to this point, we only dealt with acids.
No.
So now I want to deal with what happens with bases. It's the same idea, but yet a different twist. So, if you go back to the Arrhenius definition of acids and bases, okay? Acids are proton donors, bases are proton acceptors. They had to wait until they found the proton to come up with that definition. So again, what they found happening is that you had acid-base reactions that didn't necessarily involve your standard definitions of, oh, here's a base like potassium hydroxide, here's an acid of hydrochloric acid, hey, we're going to get potassium chloride and water out of the reaction. So let me give you a simple example. So here I have nothing but water, okay? Now, when you deal with bases, unlike waters, or unlike acids, if you wrote down the waters, hey, that was kind of optional. When you deal with bases, you have to write down the water molecule, okay? You don't have a choice. And here's the reason why. Because what's going to happen is that base is going to look for a proton. And the only place available for that is generally going to be water. Not always, but most of the time it's going to be in a water environment. So what I'm going to do is I'm going to add a little bit of phenolphthalein to it. Okay? So, not a big deal. Added some phenolphthalein. So now I'm going to add just sodium carbonate. Okay? So sodium carbonate is Na2CO3. Okay, everybody cool with that? Na2CO3. Is this going to be soluble or insoluble? Soluble. Why?
Because it's got a sodium zone.
Yes, it's got a group 1. Alkali metals are all soluble, right? So here's what's going to be important, is that when I dissolve that in water, I'm going to have some sodium ions floating around, and I'm going to have some carbonate ions floating around. Okay? So, more and more, you have to understand what the species are and what form they are in a reaction. Like, for example, with sodium. There's a big difference between elemental sodium, which is a gray metal that reacts violently with water, versus a sodium ion, which binds with carbonate and makes a white powder. Okay? Two completely different things. So sodium and sodium ions, gain or loss of an electron, make a huge difference in what's going to happen. So I'm not reacting elemental sodium in the water. It's going to be sodium ions. So the sodium ions, you'll see later on based upon reduction potentials. The sodium ion is completely happy. Okay? It's lost that outer shell electron, which was a pain anyway, so it's just happy to float around going, whatever, dude. Okay? Now the carbonate ion is a different story. So if you look on your Ka values, you can find carbonic acid. Carbonic acid is H2CO3, right? So by virtue of the fact that there's a Ka value for carbonic acid, is carbonic acid a weak acid or a strong acid? It's a weak acid. So what that means is that carbonate ion, because it's the conjugate base off of a weak acid, wants to very much reform and make carbonic acid. Okay? So it's just like, oh man, I'm missing my protons. Okay? I want to reform the carbonic. I want to reform carbonic acid. So if I take some of this and just kind of sprinkle that in there, okay? You'll notice as soon as that hits that it turns magenta. So I can take, here's the beauty of chemistry, is that I can mix two clear solutions, water and phenolphthalein, add a white powder to it, and make it turn magenta. It's magic.
It's magic.
Sorcery.
It's pretty.
Now, so by virtue of the fact that that turned magenta, what do you know about the pH of that solution? Basic or acidic?
Basic.
Basic, because phenolphthalein turns magenta in a basic solution. So here's what happened. So that carbonate ion, because of the fact that it's the conjugate base off of a weak acid, comes up to the water and goes, yo, mind if I dance with your protons? Water says, no, I don't like them anyway, why don't you go ahead and take them? Here you go, sir. So the simplest way to do this is go, okay, let's just say it takes one of them. And it forms HCO3 minus. But now that water molecule has had a proton taken off of it. So what's left behind?
OH minus.
An OH minus. So because you generated hydroxides, guess what? It turned basic because you're generating hydroxide ions. Okay? Now, if you did that with salt, nothing would happen. Because chloride, NaCl chloride ions, come from a strong acid of HCl. Chloride could care less about water. It's not going to reform hydrochloric acid because it's a strong acid. But this is the conjugate base off of a weak acid. So it goes up to the water and goes, show me your protons. The water goes here you go. So what's left behind is hydroxide ions and the solution turns basic. So when you deal with bases, this is how this is going to be written. So you have the base, and in this situation the base was CO3 minus. It might be a neutral, it might have a negative charge, it's just going to be a base, okay? The main point being is that that's going to react with water, and you're going to form an acid, so this is going to be your conjugate acid, and then you're going to form a conjugate base. Now, it's the same idea in terms of how you calculate Kb. It's still products over reactants. So it's still the concentration of your Hb plus times the concentration of your hydroxide divided by the concentration of the base. So mathematically, it has the same format as your acid does. It's still products over reactants. The only thing difference is that this one is going to involve hydronium ions, and this one's going to involve hydroxide ions. Okay? That's it. Same mathematical idea. It's just, are you making an acid or are you making hydroxides? Got that? Good with that. Okay. Now, we're going to look at a couple of different reactions. Okay. So here, this is involved ammonia and ammonium. Okay? So this would be ammonium, like maybe a solution, a powder of ammonium chloride. Okay? Ammonium nitrate, which is a common fertilizer. So ammonium is NH4. It has an extra proton. So in this situation, it's going to go up to the water, and the water is going to take away a proton to form H3O plus. And then you're going to be left with ammonia. So in this situation, what is my acid and what is my base?
Ammonium's the acid, water's the base.
Ammonia is the acid, water is the...
Base.
So H3O is my conjugate acid or my conjugate base?
Conjugate acid.
Conjugate acid. That's my acid, this is gonna be my conjugate base. Okay? Now, if you take ammonia, which is a very soluble, and we'll talk more about the properties of ammonia, it's a cool. It smells god awful, but it's a cool way to do some demos.
I don't know, I kinda like the smell.
No, you don't.
It smells clean. It smells like fire. Like if you could put fire, like it smells like pain. And it hurts.
Just stop.
I have some, I have some of the
Just-
brake
just-
smelling salts in my
just-
lip.
You don't
Smelling
like,
salt?
no, like
Yeah.
sort
I
of,
have
like
some
just a
smelling
little
I have some
laugh.
brake ones in my
You don't, it doesn't
backpack.
like, no.
This backpack might
It smells like
Okay.
cleanliness. Like
So,
a
Try to
we'll
give you
deal,
the-
we're gonna spend a lot of time talking about ammonia, just not right now. So, in this situation, if you take ammonia and react it with water,
Before basketball. No, before tennis.
you can take NH4 and OH. So in this situation, is the water the acid or the base?
Acid.
Water here is the acid, the ammonia is the base. And so this is your conjugate acid, and that is your
Conjugate base.
conjugate base. Okay? So this is a classic situation of water being amphoteric. It can act as an acid or it can act as a base, depending upon the situation. Now, here's the story. So if I were to calculate in this situation, so if this is acting as an acid, so this would be my Ka calculation, which would be my hydronium ion concentration times the concentration of my NH3 divided by the concentration of my NH4, okay? So that's for the first one. And in this situation, that's acting as a base, so that Kb calculation would be my NH4 times the concentration of my hydroxides divided by the concentration of my NH3. Okay? Cool. Now, what I'm gonna do is I'm gonna multiply these two together. Okay?
Cool.
So I'm gonna take H plus,
Doesn't one of your NH4?
oh, hold on.
Ooh, oh, they do the cancel-y thing.
Oh!
That maths. That's fun.
Did you really just say it's gonna do the cancel-y thing?
Yeah.
Yeah.
Simplify.
Look at it. It does the cancel-y thing.
Are you in calc too, Phil?
Yeah.
Alright, no problem. Is that the official terms? Those are official terms.
Yeah.
Okay?
You haven't taken calc 2 yet.
You
Cool.
don't
You
understand.
wouldn't know. Yeah.
So,
You'll get there.
and in the words of Cohen, we're gonna do a canceling thing, okay? So the ammonia concentration will drop out, my ammonium concentration will drop out, and you have your hydronium ion concentration times your hydroxide ion concentration. Now, what do you get when you multiply hydronium ion concentration times your hydroxide ion concentration?
1.0 times 10 to the negative 14.
1.0 times 10 to the negative 14th, okay? Now, what we just proved is that that also equals Ka times Kb also equals the autoionization of constant of water. So here's the story.
This is gonna get way worse. No.
That is not bad.
No. But you're gonna end up giving us like the pH of a solution, asking us for like the molarity of the hydroxide ions like 15 steps later. You're gonna make it bad.
No.
We tied something together, so that means it gets bad.
Your pessimism towards,
Not pessimism, realism.
it won't be 15 steps.
It'll be 16.
No, maybe 12.
Only
I've
12.
seen what you've done to us.
Okay. All right. So here's the significance of this. Is that since these two numbers, Ka times Kb, always equal the same number, right? So if you look at this, since these two numbers multiplied together always equal 1 times 10 to the negative 14. So let's say, for example, you have a smaller Ka value. So you're comparing two acids. One of them has a really, really small Ka value. What does that mean about its Kb value?
Big.
It's going to
Yes.
be really big, right? Because the two numbers together multiply together to equal 1 times 10 to the negative 14th. Now, here's the story. Here's the next thing. If you look at hydrofluoric acid, for example, hydrofluoric acid has a Ka value of 6.8 times 10 to the negative 4th. So if you know the Ka value of hydrofluoric acid, and this is something you're going to do in the lab, if I, just like I did here, if I take some sodium fluoride and react that with water, first off, are you going to worry about the sodium?
No.
No, it's not going to
Aqueous
care.
the whole time, so it doesn't matter.
So that fluoride has a charge of 1 minus. It's the conjugate base off of hydrofluoric acid. So what's it going to do with that water?
Something. Take a proton.
Take away a proton and form what?
Hydrofluoric acid.
And
Conjugate base.
your OH, right? Now, if I ask you to do this calculation as Cohen so aptly predicted, if I said, hey, let's say that you have a 0.1 molar solution of fluoride ions, and I want you to find the pH, okay? This is only like 6 steps. Now, here's what you have to realize. First off, are you going to use the Ka of hydrofluoric acid?
What? Say it again.
Yes.
No, you're not. It's not acting as an acid. What's it acting as?
Base.
It's acting as a base.
I had a 50-50.
And you did not choose wisely.
You will still use
I was the
it,
one who
it's
chose.
Just fine.
Ah!
No.
Wheels.
Now, here's the story. If you look in your book, okay?
Oh, because you can do the.
Oh, you can do the thing.
That's what we just no, but trust me.
Okay,
Let's describe thing and
so if you look in your book, there's a whole list of Ka values.
He's talking.
Okay? There's also there's a very small list of Kb values. You cannot find the Kb value of fluoride ions. They don't write it there. Why?
Because they're being
No.
It's very little.
Because if you know what the Ka value of HF is,
You can just divide the.
you can
one
find the
times
Kb
the-
value
By dividing by
by
1.
dividing by the
One
Ka
point.
value.
I'm still
Okay?
We'll get there.
Oh, I got it.
Stay with me. Okay. Good?
Do your assignments on time.
Keep your assignments back.
I'm not even done with
I'm
mine.
gonna retire. I'm hanging up the jersey.
I told you last.
Okay. So,
I did realize.
it's gonna be the exact same process. The exact same process. But Cohen is right, there are gonna be more steps. Okay?
That's the first time he's right.
Really?
It's on your head.
It's okay. I don't want to be happy anyway.
You signed up for this.
Yeah, but you don't have to make it
No.
terrible.
It's not
Just
that.
make AP kind of drunk.
Oh, I could, no one would pass the test. Okay, now, because it's acting as a base, are you going to use Ka or Kb?
KB.
Kb, so my Kb value
Shut up. Don't make noise.
is gonna equal my HF
I'm legitimately understanding.
times my hydroxide divided by my fluoride. Now, these are both going to be X, not a big deal. But I can't find the Kb value of a fluoride ion.
Jake can.
But I can find it
using the Ka value.
Because you know that Ka times Kb equals the autoionization constant of water. So, since the Ka of acetic acid, or of hydrofluoric acid, bless you,
Thank you.
is 6.8 times 10 to the negative fourth, right? So the Kb
That's the Ka.
is gonna equal 1.0. Oh, come on,
Hydrofluoric, HF.
running out of electrons.
But he has it as X. No, X is for the molarity, Charles. We haven't found that yet.
True?
Yeah.
Everybody cool with what I'm doing?
Yes.
Okay,
I have that.
so somebody take 1 times 10 to the negative 14th and divide that by 6.8 times 10 to the negative fourth.
1.47 times 10 to the negative 11.
Good job, Jake.
1.47 times 10 to the negative 11th is gonna equal x squared over 0.1.
Oh, because it does the.
It does the thing.
Yes, it does the thing. What
are you
talking
Now, at this point, it's just like anything else. But here's the tricky part. When you find x, are you finding the hydronium ion concentration or the hydroxide ion concentration?
Hydroxide.
Oh, so find the x. So somebody take 1.47 times 10 to the negative 11th times 0.1 and then take the square root of that.
1.21 times 10 to the negative 6.
What'd you get?
1.21 times 10 to the negative 6.
Times 10 to the negative
6.
6th?
Yes.
That's your. That's.
Now, that's your hydroxide ion concentration.
I know that.
I want to find the pH.
Well,
So
that.
you could-
So if I take the negative log of this, I can find my pOH, but my pH plus my pOH add up to 14.
I don't understand that part.
So somebody takes a negative log of that and subtract that from 14.
8.08.
Now, does it make sense that your pH is above 7?
Yes.
Because you generated hydroxide ions.
So it's
Okay.
basic.
It's a base. Yeah.
Cool with that?
Yes.
Yes.
Was that
No.
not bad?
Yes.
Yes.
No.
It's
I don't
not
know.
that bad. You just have to do some stuff to find the other things. Then-
Okay.
Yeah,
I think I understand.
Yes, Charlie, you do some stuff to find the other things.
It's like,
and you use
it's like,
that to do the
it's like the
canceling
acid
thing
problem,
and
except
find
the
it, and then you use this to do the
Yes!
Except I didn't understand this.
This makes me
Oh,
understand
that's a
more.
problem.
Oh, it's,
I'm glad I understand it now.
I thought you were saying like this.
I didn't know you got the K.
Why is your wrist, that's not
I'm
I don't
crying.
want to talk about it. Hey, that's sometimes I have to remind myself that I know it.
I started. I was laughing so hard, I felt myself tearing up. And I'm like, oh, it does the thing. Charles was like, what?
Okay, Charles, finish your previous kettle science.
Actually,
Please let that be
but
it.
it's okay. What is the A?
I need to go.
Okay, so all this is out of your textbook. So, when you get to 79 and 80, only do A, okay? Just do A on both of those. All right, I'm done. Oh, wasn't that bad.
I'm still trying to figure out how to do yesterday's.
Can I get my phone and take a picture of that?
Yeah, if you want to get your phone and take a picture of it, you can.
Hey, Kev, can you bring me 6?
Yeah, I got you.
Can you bring me 25?
I beckon you. 17. Yes.
On the upside burger, I got like, one of
You're
my
really forcing
questions. So,
I haven't even.
Why is it
I don't know, normally I stir it up. I've never done it where I just drop it in there.
I like that. That's pretty cool.
That's
It's kind of cool, it's separated.
I like how every day you have to put maybe you should put some hands in.
Okay, do I? Okay, so I can start on.
She's disgusting.
No, I can't. I You're gonna use your X's for the,
What?
for the previous one.
Oh, it's separate.
And I didn't bring
It
it
has to do, when I added that finger fading, I didn't
We're not
disturb
all
it, so I did that finger fading separate.
Okay, that's not
It's gonna be okay.
But then when I added
Bring
the
it down.
same
I put in the eye of a storm.
Kevin, you just have to be like,
They have to be the